In this video, I introduce forecast human activity using inverse reinforcement learning. Now we introduce how to use inverse reinforcement learning to solve a practical problem. First, we collect human trajectory, and then we understand the human preference. The goal is to forecast the human trajectory from point A to point B in the future. Because right now the problem is a sequential decision-making problem. To use inverse reinforcement learning, we need first to formulate the problem as the Markov decision process. In the regular Markov decision process, we have an agent at the state S takes action A and receives the reward R. And now to describe the uncertainty, so we introduce one more they call a noise measurement state. So then we define the state S as the coordinates on the ground and the action as the velocity in the X and the Y direction. The policy maps state to actions. So once we have this hidden Markov decision process, then we can generate inverse reinforcement learning model. Because the reward function R is unknown, so we need to define a reward function, say as the product of model parameters and feature vectors. This feature vector, is from the state S. So once we have this reward function, and then we can use the reward function to define probability over the trajectory S. Because this probability, just like a joint probability over the trajectory S, so we use the product of the exponential here. This reward function is a cumulative reward over the trajectory. And here, this is the normalization factor, just to make sure this probability over all the possible trajectories equals to 1. So once we have this probability over the trajectory, and then we need to take into account the uncertainty in the measurement, in the observation state as U. And then we insert this observation model into this product to get the joint probability of the trajectory S and the U. And then we use a trick to make this U to this exponential term added to this reward. Because from the formulation, this is like entropy. That means we use the entropy to reduce the uncertainty on the reward, that means on the measurement state U. So from this joint probability of state S and U, if we define this observation model as a Gaussian distribution, then we can get the objective function as the maximum entropy of conditional distribution P. That means we have this conditional probability of trajectory S conditioned on the U. Here is F prime includes two terms. One is the cumulative reward function. One is the exponential term, the entropy, to reduce the uncertainty in the reward. And then finally, we have this entropy loss function. This entropy help to pick up this trajectory with the maximum entropy. And the entropy in this F prime helps reduce the uncertainty on the reward function. Once we have this entropy loss function, then we can use the 2 steps to get the convergent model parameter theta. In the first step, we use the backward path to calculate the policy at the state S. To do so, we need from all the possible terminal states to calculate the expected Q value here and expected state value function here. And from U and V, we can calculate the pi at the S. And then we use this policy into the next step in the forward path. That means just a spread from state S to all the possible trajectories until reach the terminal state. We get this sequence of D. And then we calculate the sum of this D. And then we get the feature count and the lambda policy. Because we already know the export, this the feature count and the policy and the export policy. So we use these two together to get the gradient of the loss function, and then we update the model parameters. Once we get this convergent model parameters, and then we can estimate the reward from input trajectory. And from the reward, we can use in the reinforcement learning to find the optimal policy pi. Once we have a human policy pi, we can forecast his trajectory in the future. For more details, please check with this reference. Thank you. Bye.